Welcome to our journey into computer vision, where machines see the world. Think of it like teaching a camera to understand what's in its view. First up, we'll explore how images are processed and analyzed to mimic human sight. Let's dive into analyzing images. Think of an image as a snapshot that tells a story, much like how each frame in a video contributes to the whole narrative. Now let's explore videos, which are essentially sequences of these snapshots. Videos require us to understand both individual frames and their collective flow over time. Think of it this way: analyzing images is like being a detective with clues scattered around you. You start by looking at the obvious details, colors, shapes, and figures. Building on that, consider what these elements might tell us about the context or story behind the image. Now let's explore deeper layers: mood, symbolism, and perspective, akin to understanding characters' motivations in a book. Diving into the realm of computer vision service, imagine it as your digital eye that can see and understand images. Think of image analysis like a Swiss Army knife for visuals, describing scenes with tags, detecting objects or even faces, and identifying celebrities or landmarks. This service doesn't just stop there, it also categorizes content, detects brand logos, assigns moderation ratings, reads text via optical character recognition, and creates smart thumbnails like one showing a mountain with snow. For instance, in our example, this tool can analyze an image of a snowy mountain, adding tags such as outdoor and snow, providing metadata including dimensions and format, all while recognizing the caption, "Wish you were here." Think of it as a standalone powerhouse or part of a broader cognitive services resource. We can dive into how an image analysis tool works. Imagine it like a super smart camera that not only captures images but also understands them deeply. With the single Analyze Image function, you receive a comprehensive breakdown of everything in the picture, including descriptions and tags for specific features such as brands or landmarks. Topic: Image analysis functionality. Now let's explore its capabilities further. This tool can even recognize if there are any celebrities present within the image, although access to this data might be limited depending on privacy concerns. Topic: Domain-specific details. Additionally, it classifies objects into 86 built-in categories like outdoor or mountain scenery and informs you about the likelihood of each identification with confidence ratings. The analysis also covers elements such as colors, whether the content is adult-themed, image types like clip art, and even detects faces and brands if they are present. Topic: Analysis results. Let's start by thinking about what a smart crop thumbnail is. Imagine you're trying to capture the most interesting part of an image, like the eyes in a portrait. Smart cropping does just that by identifying and focusing on the region of interest, RY. This technique automatically adjusts to maintain the desired width and height without losing important details. It's especially useful when dealing with varying image sizes or content, ensuring consistency across your thumbnails. Let's dive into analyzing images using computer vision. Think of it like giving your computer eyes to see and understand pictures. By creating thumbnails, we are essentially teaching our machines how to capture the essence of an image in a smaller size. Let's dive into analyzing videos, a fascinating intersection of technology and creativity. Think of it this way: just like dissecting a poem to understand its layers, we break down video elements to unveil deeper meanings and enhance our insights. We start by identifying key components such as visuals, audio, narrative structure, and editing techniques, which all contribute uniquely to the overall impact. Topic: Video Analyzer for Media. Imagine a tool like a Swiss Army knife, designed specifically for dissecting and understanding video content. Video analysis is akin to peeling back layers of an onion, revealing insights with each layer through capabilities like facial recognition, with access limitations, optical character recognition, speech transcription, topic detection, sentiment labels, content moderation, and scene segmentation. Topic: Service options. For accessibility, the Video Analyzer offers a standalone free version that comes with certain constraints or can be enhanced by connecting to Azure Media Services for more robust features. Topic: Custom insights. Imagine having a tailor-made key to unlock the secrets of language and faces. Predefined models exist for recognizing everyday elements like language and celebrities, but you can create your own keys for specific people or brand names. With these tools, industries can train systems to recognize language nuances, spot animated characters, and identify brands, though facial recognition does require extra steps due to privacy standards. Topic: Creating custom models. Think of it as crafting a custom lens through which you view the world. Your models could analyze anything from organization-specific terms to unique products. This customization empowers businesses to recognize patterns within their industry, making operations smarter and more personalized. However, remember that when we dive into facial recognition or celebrity identification, we're stepping into areas needing special approval, ensuring these powerful tools are used responsibly. Topic: Responsible AI. As you build your models, consider the blueprint for ethical usage. Our responsible AI standard serves as a guide, balancing innovation with privacy and safety. This ensures that while our insights grow deeper, they remain respectful of individual rights. Video Analyzer widgets and API are like the Swiss Army knives of web integration for video insights. Topic: Video analysis. These tools allow you to seamlessly embed analysis results directly into your web pages, making complex data easily accessible at a glance. Now let's explore how automation plays its part. With the REST API, you can handle large volumes of video content efficiently by programmatically managing and retrieving analysis results. In our lab today, we're diving into analyzing videos. Think of it like piecing together a puzzle where each piece is a frame from your video. To start, you'll use Video Analyzer widgets to visually dissect the video data. As if turning on a spotlight in a dark room, these tools highlight key aspects of the footage for you. But what happens when we want more control? That's where the Video Analyzer API comes into play, acting like a magic wand that lets us customize and extend our analysis capabilities beyond the widget's reach. To generate an appropriate image caption using the Computer Vision Analyze Image function, specify description as your visual feature. Now let's explore the Smart Cropping option. It centers the region of interest in the thumbnail. Building on that understanding, to recognize colleagues in videos with Video Analyzer, you should create a custom model containing a person for each colleague, using example images of their faces. Photosynthesis is the pro skills. I'm your instructor, Oli. Welcome to our journey into developing custom vision solutions. Imagine you're an artist, but instead of a brush and canvas, your tools are code and data. Just like creating art requires understanding the basics and then letting creativity guide you, developing a custom vision solution starts with foundational knowledge in machine learning and computer vision principles. Now let's explore how these elements come together to create something uniquely functional and impactful. In today's exploration, we're diving into the fascinating world of computer vision. Think of it as teaching a computer to see and understand images like humans do. First up is image classification. Imagine sorting your photo album. You categorize photos based on their content. Now let's explore object detection, which involves locating specific items within an image, akin to playing Where's Waldo, but with algorithms. Let's dive into image classification. Imagine you're sorting through a pile of assorted candies by color and shape. That's akin to how computers categorize images. By identifying key features within an image, algorithms assign it to predefined categories like cat, car, or tree. This process is pivotal in various applications, from facial recognition systems to self-driving cars. The Custom Vision service empowers you to train models using your unique images, catering specifically to tasks like image classification and object detection. Think of it this way: just as a chef needs ingredients to prepare a dish, the service requires two types of resources: training resource and prediction resource. For training, you need cognitive services along with custom vision training, while for making predictions, you use cognitive services paired with custom vision prediction. Essentially, first, you create your model by feeding it images you provide, then leverage this trained model to predict labels on new images. Image classification involves training a model to predict the class label for an image. In simpler terms, it's about identifying what the picture depicts, whether it's an apple, banana, or orange. Think of it like teaching a computer to recognize fruits by their appearances. Training an image classifier can be like teaching someone to distinguish between different types of fruits by showing them labeled pictures. First, you start with creating a project in either the custom vision portal or using their API/SDK for your preferred programming language. Think of this step as laying down the foundation where everything begins. Next, create or retrieve class tags. These are like categories such as apples and oranges. Once you set up your categories, upload tag images that will serve as examples to train your model. Finally, let's move on to training the model itself. It's akin to running a practice test with all your labeled pictures to fine-tune its recognition skills. Let's dive into classifying images using custom vision. Start by creating your own classification model, which is like teaching a computer to recognize specific objects or themes in pictures. To make this happen, you leverage the power of the custom vision SDK alongside a training resource to teach your model. Once your model knows what it's looking for, use the prediction resource to have it identify images on its own. It's as if you're handing over a set of glasses that helps the computer see exactly what you want it to. Imagine you're looking at a cluttered room and trying to find your favorite toy. Object detection is like having an AI-powered magnifying glass that identifies and highlights specific objects, like toys or furniture, from any image. It involves algorithms that can recognize patterns and features of different items, allowing computers to see and understand images the way we do. Now let's explore how object detection models are trained to spot these elements. Object detection involves training a model to not only identify but also pinpoint the location of different objects within an image. Think of it as giving your camera the ability to read and describe its surroundings by recognizing items like apples, oranges, or bananas and their positions. It's about answering the question, what objects are present in this image, and where exactly? Topic: Training an object detector. Start by navigating to the Custom Vision portal or using the Custom Vision API/SDK, available as REST APIs or SDKs for various languages. First step involves either creating a new project or retrieving an existing one. Next, manage class tags by creating or accessing them, setting the foundation for your object detector. For each image you'll work with, identify and list regions. These are essentially bounding boxes that pinpoint objects within the images and label them with corresponding tags. Once tagged, upload these images to commence training your model. Topic: Image tagging. Let's start by understanding how we can label images with tags. Think of it as giving your digital photos a set of descriptive stickers, where each sticker specifies an object in the photo, like an apple or banana. The easiest way to do this is interactively using the Custom Vision portal, which even supports smart labeling once you have some initial training done. However, remember that for everything to work smoothly, you must export your tags in a specific format that matches the image size proportions. Moving forward, while there are other tools available for tagging, sticking with one ensures consistency and accuracy. This is crucial when coordinates and measurement of objects within images need to be precise as they relate proportionally to the overall image dimensions. Think of it this way: detecting objects in images is like teaching a computer to spot specific items, just as you would point out objects when playing I Spy. We start by creating an object detection model using Custom Vision. Building on that, we integrate the Custom Vision SDK with a training resource to teach our model what to look for. Next up, we use the SDK with a prediction resource to test how well it can identify these objects in new images. Imagine you have photos and want to sort them into cat or dog. For this, you'd create an image classification, multi-class, custom vision project. Now let's explore where to host your trained model. The right choice is Cognitive Services. Before using the Smart Labeler tool for object detection models, you must train an initial object detection model by tagging images with objects of each class. Let's delve into how ecosystems work, similar to a finely tuned orchestra where each instrument plays. Welcome to today's session on the fascinating world of facial recognition technology. Detecting faces in images or videos is like a game of hide and seek where our eyes search for those unique patterns. Now let's explore how we analyze these detected faces, breaking them down into key features such as eyes, nose, and mouth, much like solving a puzzle by identifying each piece's shape and position. Building on that, recognizing faces involves comparing these features to known profiles, akin to finding the right match in a deck of cards. This technology powers various applications from security systems to personalized services. Imagine teaching a computer to spot faces in a crowd. Detecting faces using the computer vision service is like equipping it with superpowered eyes. This agenda focuses on harnessing the power of the face service for this task. Imagine you have a magic camera that recognizes people in a crowd. That's what computer vision does for face detection, using algorithms to find and identify faces in images or video feeds. It analyzes pixel patterns much like how our eyes spot familiar features, making it possible for technology to interact with the real world in new ways. Imagine your camera app automatically recognizing who's in a photo. That's the magic of face detection, which is just one aspect of computer vision services. Let's explore further with limited facial feature analysis. Think of it as identifying where faces are and basic attributes like location and head pose. Now we delve into something more advanced, comprehensive facial feature analysis for precise comparisons and verifications. Building on that, facial recognition takes things to the next level by not just analyzing but actually recognizing who's in front of you, a capability requiring special access approval. Think of it this way, face detection and facial recognition are like keys that can open many doors, but they must be handled with care. These technologies need strict guidelines to ensure they respect privacy and fairness. Microsoft enforces a limited access policy for these features, meaning users need approval before use, ensuring data is used responsibly. It's crucial that systems protect individual privacy, informing users about how their images are utilized and who can access them. Moreover, the technology must be inclusive and fair, avoiding any prejudicial impact on individuals. Imagine the power of computers seeing faces just like we do. Using Microsoft's computer vision service, you can detect faces in images by leveraging the Analyze Image function. Here's how it works. Specify faces as a visual feature and the service identifies faces along with details such as age and gender, though note these features are now deprecated for new customers. For instance, consider an image where one face is detected at coordinates, top 225, left 237, with dimensions 130 by 130 pixels, and another at top 309, left 534, sized 119 by 119 pixels. This technology enables various applications, from enhancing security systems to personalizing user experiences. Imagine using a digital magnifying glass to zoom into faces within images or videos. That's essentially what the face service does. It identifies, detects, and analyzes facial features with remarkable accuracy. Think of it as your own personal detective tool in the realm of image processing, helping applications tailor experiences by recognizing who you are. The face service is all about understanding the human face through technology, much like how a detective uses clues to solve a mystery. Think of it as a tool that detects faces and analyzes features such as noses, eyes, and mouths to perform tasks like facial recognition and comparison. It even deals with challenges like blur or occlusion. Now let's explore its components: detection, attribute analysis, and landmark location. These elements help in identifying attributes and comparing faces, akin to distinguishing twins by their unique marks. Imagine each detected face is like a unique puzzle piece, given an anonymous ID such as ZYXW09876 for easy identification. These IDs are stored in your service resource and last for 24 hours, allowing you to compare faces across multiple images. This capability lets us verify if two faces belong to the same individual or find similar features between different faces with IDs like ABCD-12345 and BO 54321. Let's start by understanding how we can train a facial recognition model using face images. First, create a person group for the individuals you want to identify. Think of it as setting up your own exclusive club where each member has their unique attributes. Next, add a person for every individual in this group. Consider them as profiles or entries in your club's directory. You then need to upload multiple detected faces for each person, which becomes what we call persisted faces. Building on that, the next step is to train the person group so the model can recognize and differentiate these faces effectively. Once trained, you can use this model for tasks like identifying an individual person or verifying their identity using their face, just as a bouncer checks IDs at your club's entrance. Additionally, it allows you to find similar faces to a persisted face, helping in scenarios where you might need to recognize a new member who looks similar to someone already in the group. In the realm of computer vision, detecting and analyzing faces is akin to teaching a machine how to recognize different people. Think of it this way: just as our eyes scan for familiar features when we meet someone, these services scan digital images to identify human faces. Now let's delve into how exactly they do that. The computer vision service first detects the presence of any faces in an image. Building on that, the face service takes over to analyze and recognize the unique attributes of each detected face, much like identifying a friend by their smile or eyes. In assessing which facial attributes can be predicted, the computer vision service offers insights into eye classes and occlusion but not location. When identifying named employees via facial recognition, the face service is your go-to option. For verifying patient identity across different hospital photos taken close in time, comparing face IDs from reception to ward photographs ensures consistency. Let's dive into understanding ecosystems, which are like intricate webs of life where Welcome to our exploration of reading text in images and documents. Think of it as a detective work where your computer becomes the magnifying glass, helping you uncover hidden text within images or documents. This process involves using optical character recognition (OCR) technology, which scans images to recognize and convert any embedded text into digital form. Now let's explore how this fascinating technology works, making text in photos, scanned documents, or even handwritten notes accessible for editing and searching. Building on that understanding, we'll see how it bridges the gap between visual content and textual data. Think of computer vision as a digital eye, capable of reading and interpreting images just like we do. Topic: Computer vision. This technology allows computers to understand visual information directly from photographs or video feeds. Now let's explore how the form recognizer service works. It acts much like an intelligent scanner, extracting vital details from documents efficiently. Imagine your computer as an expert reader, scanning text just like you would read a book. This is what the computer vision service does. It helps machines interpret and analyze printed or handwritten words on various surfaces. Now let's explore how this technology can be used in real-world applications, such as automating data entry or even assisting visually impaired individuals by converting physical documents into digital text. Let's dive into the capabilities of the Read API, which is designed to extract text from both images and PDF documents. This API uses a newer model that offers greater accuracy compared to its predecessors like OCR. It excels in reading printed text in multiple languages as well as handwritten English text. Now let's explore how it works. The Read API employs an asynchronous programming model. Unlike older methods, this means you will need to poll for results instead of waiting for a synchronous response. This design choice is crucial for handling large documents or images efficiently. Let's explore how to use the read API effectively. Start by calling the read function to obtain an operation ID. Once you have this, proceed to call the getReadResult function using that ID to retrieve your results. These results will provide details such as the URL or binary image data of the process content, along with metadata like creation and update timestamps. The response also includes a detailed analysis of each page, specifying attributes like language, angle, dimensions in pixels, and text lines. Each line of text is further broken down into individual words, complete with their bounding boxes and confidence scores indicating the accuracy of recognition. Imagine you have an image with text, like a treasure map, and you want to read that text without manually deciphering it. That's where the Read API comes into play. Think of it as your digital magnifying glass for scanning images. This tool converts those images into readable text formats, opening up new avenues for automation and accessibility in your projects. Imagine your computer as a detective, capable of extracting clues and information from forms just like in a mystery novel. The Form Recognizer service acts as an intelligent assistant that reads and understands documents. Now let's explore how this technology identifies key data points from various types of forms with precision. The Form Recognizer service is a powerhouse for extracting data from various forms, offering pre-built models for standard document types like receipts and invoices. Building on that, you can train custom models tailored to your specific needs using either unsupervised methods with unlabeled data or supervised techniques with labeled data. Provision options include setting it up as a standalone form recognizer resource or integrating it into a broader suite of cognitive services. Now let's delve into the world of pre-built models REST API. This service allows us to analyze various documents such as receipts, invoices, and business cards efficiently. For instance, consider a receipt from Fort Coffee that lists items like a latte and cake with specific prices. Using this API, you can extract key details such as merchant name, transaction date, and total amount from the receipt seamlessly. Similarly, for an invoice from Contoso, information like vendor name, invoice number, and items can be retrieved swiftly. This functionality extends to business card as well, where names and contact details are extracted with ease. Training custom models without labels, also known as unsupervised learning, is like teaching a robot to recognize patterns without being told what those patterns are. First, upload at least 5 sample images or PDF forms into an Azure Storage Blob container. Think of this as providing raw materials for training. Next, generate a shared access security (SAS) URL for the container, which acts as your key to securely access these materials. Then, initiate the training process by using the Train Custom Model API with your forms, much like starting a recipe. Finally, retrieve the Train Model ID using the Get Custom Model API, akin to checking off a completed task. When training custom models, we need labeled data, akin to how a child learns from being told what each object is. First, store your sample forms in Azure as JSON files. These contain crucial layout and label field information. Next, create a shared access security (SAS) URL for this container. It's like getting the keys to a secure building where all your data lives safely. Now, utilize the Train Custom Model API with the useLabelFile parameter set to true, which directs the system to use these labels during training. Alternatively, you can retrieve your Train Model ID using the Get Custom Model API, much like checking in on how well your model has learned its task. Or for a more hands-on approach, employ the sample labeling tool to manually label and train data, offering precision and control. Diving into custom model usage, begin by invoking the Analyze Form function to generate a result ID. Following this, utilize the Get Analyze Form result function to fetch detailed results, including body elements such as source, result ID within the analyzed results, and metadata like created date time. The analyzed result, structured in version 2.0.0, may include read results with bounding box information when include text details is set to read results. Depending on the model type, unsupervised or supervised, the results are organized under page results for fields from unsupervised models and document results for those derived from supervised ones. To extract data efficiently, start by training a custom model using unlabeled forms. This allows the system to learn general patterns without human input. Now let's explore how labeling these forms can refine your model further. By adding labels, you provide specific examples that enhance accuracy and reliability in extracting relevant information. Topic: Extracting text. Think of scanning a letter as capturing an image that holds hidden text beneath its surface. To reveal this, you should use the Read API of the Computer Vision Service, which is like having a magic magnifying glass to decode and extract the text. Topic: Submitting expense claims. Now let's explore building an application for expense claims. It needs to understand details like merchant names, dates, and amounts from scanned receipts. Here, the Form Recognizer service shines as it specializes in interpreting complex documents with varied data points. Topic: Cargo manifest. Finally, when dealing with cargo manifest forms where only specific fields matter, employ a pre-built model using the Form Recognizer service. It acts like a precise filter that hones in on and extracts just what you need.